These are some examples of recent modeling work that my students have done. Stress around TSV, analytically describing stress around TSV, doing electromigration experiments, developing geometry-based models for uh, modeling those electromigration experiments. These models need to have surface diffusion, which is fairly challenging to include in any sort of model like this. And then other electromigration-driven failure mechanisms. This was sponsored by Intel and SRC project, customization project. We also worked on back end of line fracture problems, what we now call as chip package interaction problems, before the term was coined. This was back in 2009. We started this project. We explained why certain layers cracks would originate at certain locations and what drove them during the reflow process. And we've also more recently developed computational modeling schemes to bridge multiple length scales. Generally, finite element models are very poorly suited for these kinds of length scale bridging because the mesh needs to span the entire length scale. That makes it challenging. So we developed alternative techniques where you can mix and match meshes of different sizes and even computational tools, different commercial tools. And then finally, some reliability models where we've developed first principles models for predicting accurately life. We also do experiments, including package characterization, electromigration characterization, indentation experiments to extract properties by inverse methods, thin film adhesion characterization, and more extensively, micro and nano precision mechanical testing of materials. We've tested pretty much all the solder materials. Okay, so that's a little bit about my background. And today's outline, I'm going to start with introduction to modeling, data, and fits. A lot of this is going to draw on my systems and design training as well as my numerical analysis training. And then I'm going to switch over to more physics, explaining the governing theory for the class of problems we have undertaken to study now. Those are reaction diffusion problems. I'll talk about the computational modeling of those reaction diffusion problems. And then I will talk about these two topics. The second and third bullets are more physical modeling. And then I'll talk about, can we abstract them into ML models? What are the challenges with building ML models? Can ML models be useful? Again, more provocative questions here for the benefit of Victor. And then finally, I'll talk about one example, ML for 3D package electrical thermal co-design, and summarize. So that's going to be my talk. I'll launch into first into introduction into modeling, data, and fits. Many of these are things that we know already, but nevertheless, I thought it would be useful to level set us. Let me start with an example. Generally, engineering functions, anytime we have to evaluate performance, that's what I mean by engineering function. From a mathematical perspective, it's a function. Any performance evaluation is really an evaluation of a function, a mathematical function. Those are expensive to evaluate, and any sort of analytical effort that one can put in is worthwhile. Here's an example. This is a bone, how bones adapt to mechanical loads. We know that our thigh bones, for instance, femurs adapt to mechanical loads, and it's important to understand how they adapt to mechanical loads, because if you want to design prosthesis, you need to understand how bone adapts to prosthesis. So I developed a model many years ago on before this topic came to be known as topology optimization. What we were trying to do was to optimize per this criteria developed by McNeil Alexander. I highly recommend this book. It's a beautiful book on how you can mathematically model many aspects of animal behavior as well as structure. So what we did was every one of these elements here, finite element, it actually has a density that varies within a limit. And you can optimize that density per the criteria. And in bones, it's known that the density is related to stiffness modulus as well as strength. So using that, you can come up with this sort of a optimized structure. And if you were to do this by finite differences, because you need to calculate not just the function value, but also the derivative of this. And if you were to do this by finite difference on a IBM 9370 mainframe that I had access to at that time, one sweep of variables would take 16 hours, whereas you can reduce that to just 3.5 minutes if you used analytically derived sensitivities. It takes more effort to derive these sensitivities, these derivatives analytically, but it's well worth it because it can reduce the time it takes to do a physical model from 16 hours to a few minutes. So that's why the first point that I'm going to make is functions are expensive, analytical effort is worthwhile. Second is synthesis always requires expensive analysis. If you have any sort of engineering system optimization, there are two aspects to it. There's a synthesis aspect where we are using optimization algorithms to search. Given the current state, we want to find an improved state or improved set of variables. And so we use optimization algorithms, typically nonlinear programming algorithms in the synthesis step. And this in turn requires us to evaluate whether our current set of variables are good enough. For that, we need analysis. Typically in mechanical design context, also in electromagnetic context, we would use finite element analysis. And if we could, we would do design sensitivity analysis, which gives you derivatives in much more efficiently than brute force finite differences. We also need to pay attention to design representation. And I'm going to skip the last point. What we are trying to do is, because analysis is expensive, we want to replace this finite element analysis box here with surrogate models. Oftentimes, these days we hear a lot about ML models. ML is only one of many possible surrogate models that one could use for replacing this analysis because analysis is expensive. Now, we need to keep in mind that effective synthesis or control algorithms are first order methods. All these optimization algorithms are reliant on first degree derivatives. They are first order methods. Therefore, accurate functions as well as derivatives are needed, not just functions. So please keep that in mind. And I'll come back to this point later, whether ML is always good for calculating derivatives. So let me then start with a classification of data used for surrogate model generation. This is my classification. It's not something that is commonly, this is something that I put together. So this may not, you may or may not agree with this. So if I develop data from systematic experiments, which is what we do most of the time in industry, in my few years in IBM, we are mostly reliant on DOEs, designed experiments. So we develop experimental data. Now, we also sometimes do random tests, and I would call those data points empirical data. If you rely on computational models, I would call that simulation data. Computational model has to be grounded on theory. Therefore, theory has to feed into computational models. But now sometimes we can directly take the theory and generate data by solving the theory analytically. In that case, you have analytical data. This is the best of all of them, in my opinion, because this is the least expensive to generate the analytical data. Now, once we have physical data, we can also create synthetic or generative data, and together they form the training data, and the training data can then be used to develop ML models or digital twins, if you will. And then when we compare the models to physical data, we get the model error that drives, again, the model development. So this is, again, to level set all of us on what I mean by data. Now, I'm going to talk a little bit about a topic that is very well studied in CAD literature, in geometric modeling literature, and that is the idea of interpolation versus approximation, and this notion that they have both local or global control. Let's take, for example, a simple function like the one that I show here. F of x is x e to the power 2x sine of 2 pi x. And I'm looking at a small region of that function. What I then did was to generate data points based on this function, added noise to it to generate these 10 data points. So I actually gave this as an exercise to my group over the last week and have them generate different fits to the data points. and more for their education. So let me start with what I call as interpolation fits. Interpolations pass through every point. And I'm also going to do something else. I'm going to move one of these data points. After I fit, I'm going to move one of these data points to see how the fits change. The first thing I want you to notice is if I take these 10 data points and fit a degree 9 polynomial through those 10 data points, and they would be highly oscillatory, these dashed blue lines. You can't even see it within the scale of the plot that you see here. So polynomial fits are usually not a very good idea. And then you can see, this is the original curve, the black curve. And then you can see the neural network prediction. That's the green line. And you can see how that changes as I move this data point. And you can see that what is a fact that is well known for neural network is that it always overfits the data. So it's not necessarily always the best way to fit data because it overfits the data. Now I'm going to move on to approximation fits. I'm going to use different methods, not just a polynomial fit. Now I have a 90-degree polynomial. Instead of interpolating through every one of those points, I'm going to fit an approximation of degree 2, degree 3, degree 4, etc. And I'm also going to fit a spline, a B spline here, degree 3, degree 2, degree 3, degree 4 splines. And you can see that you can many times get much better representation of the original curve with an approximation. Here, for instance, the degree 3 spline, you can see actually does a decent job compared to our degree 2 or degree 3 splines does a far decent job compared to what you would get with machine learning methods. So, and now if you look at the derivatives, I said that you need derivatives previously. If you look at the error in the derivatives, you'll find that the highest error is with neural networks because they tend to overfit the data. So again, interpolation versus approximation, local versus global control. Local control is when I move a point, I want the influence to change only in the local region. I want the curve to change only in the local region. Yeah, global control is what you have here with neural networks. When I move the points, what you find is a neural network, the entire curve changes. Whereas if I look at, for instance, the other curve here, the piecewise Hermitian, it has more local control. So you always want local control more than global control. There are techniques that are used in the CAD literature. I talked about B-spline. A more popular one is a non-uniform rational B-spline. This is used widely in CAD systems. Almost all the geometric models we build are non-uniform rational B-splines. They're actually splines of what are called Bezier curves. And so these are fairly very popular, and they are smooth, they are approximations. The points that you see here are control points, and they are splined at points to ensure derivative continuity. Another point that I want to make here is more data for synthesis or control is not necessarily better. This is very well known again in the design community. If I want to, say, model an elliptical shape, and if I mesh with the finite elements this geometry, and I use the nodes of the mesh to control the shape, you would end up with shapes that look like this, which don't quite look smooth or elliptical. So therefore, fewer data points, fewer control points, better approximations like the B-spline is better. It's something that's well known. And I'm going to give you an example of that. I'm going to now start to switch towards electronics packaging related examples. Solder droplets, I'll start with solder droplets. Solder droplets shapes are, are really ones that minimize surface energy, and this is gravitational energy and some externally applied forces subject to some volume constraint. So if I have two pads that look like this, misaligned, offset, and then you can actually predict the shape by controlling every point here. This is what we developed here, procedure we developed here by optimizing the location of every nodal point on the surface. I can come up with a shape, and then I can figure out a way to mesh in 3 dimensions the solder droplet, analyze, and figure out its elastic plastic creep behavior. Now, I can do the same optimization and get much nicer, smoother shape by representing the surface with non-uniform rational B-splines. is a much better representation than allowing each node to vary, because here I assure derivative continuity, whereas when I use finite elements only assure C0 continuity. There is no derivative continuity in finite elements. So this is an example. Another example, you can take that same sort of modeling tool, run it many, many times over to estimate fatigue life, and you can capture it in basically a GUI like this. Behind this is a machine learning model, a neural network model. Back in those days, we didn't call it machine learning, we called it neural network. Behind this GUI is a neural network model which can quickly estimate fatigue life given shear displacement, axial displacement, etc., the controlling displacement parameters that you see pictured here. So you can do that sort of estimation. Okay, so another point about models, the model complexity needs to be fit for purpose. So generally, this is design-oriented models. You want computational time is premium for design-oriented models. So you're willing to compensate, you're willing to compromise on model fidelity when your goal is design. On the other hand, reliability or process models need to have much more fidelity. Therefore, they need more computational time. Here, for instance, I'm showing you a fatigue crack growth model on a solder joint compared to actual experiments. If you want this level of fidelity, which is very rare in fatigue life estimation, your model needs to be fairly detailed, and you cannot be focused on computational time alone. So model evaluation speed is more critical than absolute model fidelity during design, but process or reliability models need high fidelity. And last point, this is a slide that I borrowed from Sebastian. Thank you. So Sebastian is online, thank you. So we need multi-scale models in addition to multi-physics models. We recognize multi-physics models as being important because we're dealing with electrical, thermal, mechanical effects, but models also need to span from possibly angstrom to millimeter length scales, 5 to 8 orders of magnitude if you want to span materials to packages. Okay, so that's about general discussion about modeling. Let me move on to now talking about specifics of the kinds of models that we are having to deal with in the problems we are dealing with. So here is a slide from the proposers day in mid-May. So these are the processes that we have set out to model and develop digital twins. These processes involve phase transformation, addition or removal of material by reaction and or diffusion. These are generally classified as reaction diffusion problems. And these problems are fairly challenging, both from a theory point of view and from a modeling point of view. My experience is more in the packaging, advanced packaging, but nevertheless, these class of problems are general. So I'm showing some examples from packaging literature. This is an electromigration. This is actually an example of reaction diffusion problem because the voids that form because materials being moved from one location, from the cathode location, from near cathode to the anode location. Corrosion is an example of reaction diffusion. The intermetallic formation is really an example of reaction diffusion problem. And the example failure problem that I showed earlier is also an example of reaction diffusion problem. So these are problems with complex interface geometry. These interfaces are very complex, and they are micron or smaller length scales, and therefore surface phenomena dominate in these problems. And you see, if we are doing semiconductor processes, I imagine that the length scale that's of interest to us is probably nanometer to micron length scale. And diffusion of multiple species, both in the bulk and on the surface, is important. Stress in both bulk as well as non-homogeneous anisotropic surface stress that could occur at these interfaces, those are important as well. So these physics have to be somehow captured in the model. In general, the theory for describing what is happening at an interface is not very well developed. If you look in the literature, there are very, very few because the math is complex, because the interfaces are arbitrarily complex in geometrical shape. Therefore, you need to bring in concepts from differential geometry. You need to have concepts of projected gradients, etc., which becomes much more messier. And you need to account for quantities that may actually move from one phase to the surface, some may pass on to the second phase, some may diffuse on the surface. You need to account for all of that. So for all of that, well, you need what is called an interface transport theorem. It's the first step to deriving the balance laws. I won't go through in detail what this is. It's all published work from group. But essentially what this does is taking a small region in the interface, collapsing that interface into what's called a pillbox, and accounting for what's coming in and what's going out and what's staying on the surface. And then you can actually use this to derive balance laws on an interface such as species mass balance, momentum balance. And it turns out the momentum balance, the general form is here. But if you have an isotropic surface stress, any interface has a surface stress. If the surface stress is isotropic, then you can actually derive back the Laplace-Young equation. You can actually obtain the Laplace-Young equation, the well-known Laplace-Young equation, and you can get the entropy inequality. I'm going to skip through this somewhat quickly because this is somewhat detailed theory. And you get the second law condition. And from the second law condition, you can derive this condition at an interface. This is fundamental condition, has well-known mechanics history. Some of these quantities together is what's known as the Eshelby energy momentum tensor. You can derive that quantity, and you can derive on the surface. This is on the surface, an entropy definition on the surface relating to the surface free energy. And you can also derive a surface fixed law, so a surface Fourier law as analogs to the bulk quantities. These are all at every point on the interface between two phases. The phases could be solid, liquid, or whatever. So, okay, then let me move on to computational modeling of these reaction diffusion problems. Interface evolution is fairly challenging to model. In general, here, for instance, is an example of a solidification model that we've done in the past. So again, now what you're dealing with is an evolving interface. If you're using mesh-based techniques like finite element techniques, as these interfaces evolve, you need to remesh. So that's not very viable. And so oftentimes we rely on fixed mesh techniques where the background mesh is fixed, but the interface evolves. A classical example of that is what's called the XFEM method. But here we've developed alternative explicitly modeled method, which we call as enriched isogeometric analysis we've developed in the past. So with that, let me go on to the next slide and explain what's the difference between implicit versus explicit simulation techniques. These are what we need to bring to bear to do the simulation of etching, deposition type processes. So here, for instance, if you have an implicit boundary is usually when we have information where we can tell whether we are on one side of the boundary or the other, but we don't quite track the boundary itself. So this is a classic example of implicitized boundary is when we use phase field or level set methods. And the other is the technique that I described, which is developed in my group, which is based on what is called an explicit boundary method, which we call an enriched isogeometric analysis method. Here, at every point, we know exactly where the boundary is. The boundary and physical phenomena that's associated with this boundary enriches the underlying field. If you use this method, there are some advantages. The governing equations are far simpler compared to what you would get. This is just solidification problem, which is one of the simplest problems one can think of. You can see the messiness of the phase field governing equation and the boundary condition that you apply. So, and you can get higher degree smoothness here at every point on this interface, normals and curvature, etc. There are some advantages. Here are two examples of methods that we've used. These are phase field solutions, but we've also done sharp interface methods as well for solving these problems. Here, for instance, voiding and IMC growth in solder. The left-hand side is electromigration voiding with anisotropic diffusivity. In this case, the diffusivity is greater in this direction. In the second case, the diffusivity is greater in the horizontal direction. You get different void shapes. And here we are looking at studying the stability of the IMC growth. These are all published work. So in here, it's a trade-off between rate of reaction versus surface diffusion. If surface diffusion is low relative to the rate of reaction, then you get these scalloped shapes that you see initially in these copper 6 tin 5 formation. And then if, on the other hand, surface diffusivity is high, then that flattens out into a flatter surface that you see longer term in copper 6 tin 5 intermetallic. Okay, so that's about physical modeling. So I know I have a lot. So I'm going to move on to talking about ML models. First, I'll ask the question, are ML models accurate? So this is the reason why I didn't share the slides with you ahead of time, because there's a major typo right there. So I'll correct that and send that to you, Victor. Um, so let's start with the first test problem. I'll start with, in general, in nonlinear programming community, we use test problems to evaluate algorithmic efficiency. So one of the most common test problems is this Rosenbach's function. It's a two-variable problem. It looks very simple, but it's actually a steep banana-shaped valley, and it's very hard for algorithms with which are not super linear to converge to the solution. So there are two functions. One is paraboloid function, the other is Rosenbach's function. And let's take these and see how well we can fit a machine learning model to these simple algebraic functions. We also have other types of test problems, structural problems, because these are more physical. And so I'm going to show you how well machine learning models do on these problems. So here's a paraboloid function. Here is the error in the function obtained when using the machine learning model as a surrogate for the exact function. This is the neural network that was used. We tried different neural networks, and you can see the error in variables, pretty good, 0.2%. It's not too bad at all. And then you can see the training time was 0.5 seconds. So this was on a PC with 128 megabytes of RAM, was done in late 90s. So we can do far better now. And the optimization time or the inference time is much less compared to classical optimization. Now, if you total these two, you'll find that the classical derivative-based optimization actually does better than the total time it takes for training and optimization using machine learning. Let's take the Rosenbach's function. Look at the error in the function. Error in function is 64%, huge. Look at the error in variables, pretty significant as well. And look at the training time, very large. Even with that, you get large errors. And the classical optimization can achieve that in 0.44. The message is ML models are only as good as the input data. You need infinite data to get high fidelity ML models. What about physics-informed neural networks? PINs. This is more recent. It's unpublished work. So here is a very simple heat conduction example with Dirichlet boundary conditions on four sides. We have the heat conduction equation, and we tried different pins architectures with single hidden layers, two hidden layers with varying hidden neurons, and there is a reference FE solution. What you'll find is that pins actually need to go much further in order to be able to get to be as efficient or accurate as a finite element solution. So again, machine learning models require high degree. A number of the data points that you need is very high. And even so, alternative techniques like pins are still, in my opinion, unproven. So can machine learning models be useful? The answer is yes, absolutely. And I'll give you an example. This is, again, a little bit of a story behind this. I was in IBM, and then I went and joined University of Colorado. IBM printing division was based out of Boulder in Colorado, and they had room-sized printers, and they were required to provide to their customers what are called ICC profiles, International Color Consortium profiles. So IBM was kind enough to give me a grant to develop color consortium profiles for their room-sized printers. So I was learning about physics of color printing. And the way it works is you have an image on your screen, and the customers want to make sure that when it's printed in a printer, that image looks as accurate as it was on the screen. So normally the way it's done is because the color representation on the screen monitor is very different from color representation on a printer, you convert the color representation on the screen to a standard color space or device independent color space. Most common is what is called the LAB color space. There is also an XYZ color space, as it's called. And this is a three-dimensional space. Any color can be represented in this three-dimensional space. And then you map it to what the printer can produce, which is closest to the device-independent color space. Again, that's an optimization problem. And so here is a representation of this XYZ color space. So printers produce colors subtractively, as it's called, and monitors produce colors additively. So monitor color representation will typically tend to be a triangular representation, red, green, and blue, red, green, and blue being the ones between which the colors are interpolated. Printers, on the other hand, are printed on a white paper. They filter out colors that pass through, so they would tend to be hexagonal in shape. So what you're trying to do is, given a color, you're trying to map it to the corresponding closest point in the printer gamut. Given a monitor color, you're trying to map it to the closest point in the printer gamut. And as you can see, the gamuts are not the same. The range of colors that you can produce with the monitor and the printer are not the same. So the mapping problem becomes an optimization problem. You're trying to find the closest point in the gamut of the printer. And different printer, this is the IBM room size printer, you can see that the gamut is not as extensive as you would have liked compared to the monitor. You want them to be overlapping exactly, but because of the nature of the way in which the colors are produced, they don't match. So it's an optimization problem. And what we did was to develop a machine learning model for this gamut mapping problem. Like I said, it's minimizing this Pareto optimal problem, Pareto optimization problem, subject to constraint that the error in color has to be bounded and subject to the maximum amount of ink usage and maximum amount of black usage as well. So this is a Pareto optimization problem. The C1, C2 represent the preference of the users. We actually patented it and it was licensed. So the way you develop this sort of machine learning model is you print swatches. You print thousands of swatches. You physically characterize every swatch's LAB, and then you build a machine learning model. And that machine learning model now becomes a base, which you can modify if need be, if the printer goes out of whack, for instance. So we did this, and here is, an example of how this sort of a machine learning model can be used for color mapping with different amounts of error, allowed error, or different amounts of ink. If you want less ink but similar error, you get an image like this, etc. So again, this is all published work. So here is an example where machine learning actually worked. Why did it work? Because we were willing to invest the time, extensive time required to build this machine learning model by printing thousands of color swatches, color patches. So if you're willing to do, we actually characterize 7,000 color patches here in order to build this accurate machine learning model. So that's the message of machine learning. So let me last talk briefly about ML for 3D package electrical thermal core design. This is joint work with my colleague Dan Jiao at Purdue University. So here again, I want to bring out an important point. So if I need thousands of data points for building accurate machine learning models, then I need to somehow automate data generation. If that data is based on physical models, I need to automate the way I develop the data, the way I generate the data. Here in this particular study, what Dan and I were able to do, we had developed, in my group, we had developed a finite element code, which could automatically describe any complex three-dimensional layered structure like a 3D package. And then we could actually apply boundary conditions and analyze it. We were able to automate that process, and that required some data structure to represent three-dimensional layered structures, which was a topology graph. And then we built the geometry and meshed it. We assigned power maps. We were able to now, we assigned random power maps, assigned random boundary conditions, solve using the tool that we had developed for arbitrary chiplet placements. For here, lots and lots of chiplet placements that Dan's student developed. Then we were able to solve it, interpolate the solution, right, develop a new machine learning model, and use that to train. So that's what we did. And this was the machine learning model that was developed by a colleague, Jiang Chu. So he's the expert. So he developed this image. He used this image to image translation idea. The idea was at every point in the three-dimensional structure in the node, you can think of that point as basically a pixel, and then you can use this image-to-image translational neural network architecture to develop a machine learning model. And details are described in the paper that's here. And how well does it do? Here is the original power map. Then it's converted into, this is the conductivity of this three-dimension. This is actually a 2.5D stack, but it with an encapsulant on top. So complete encapsulation on top. We can automate arbitrary, for every placement, we were able to generate the mesh and analyze it automatically in a few hours. So we were able to do this 4,000 data sets in a few hours. Apply boundary conditions, random boundary conditions. This is the finite element solution. Prediction, difference between them is the error. And you find that generally you can do quite well. How well? The root mean squared error in temperature is 2.5 degrees Celsius. Peak error is about 10 degrees Celsius. The maximum percentage error is 0.53. So you can do quite well on an average. And the time, test time is 0.0035 seconds. So you can do quite well. But where you see the errors are where there is actually a jump in conductivity. So that's where you get the error. So this is, again, electrical thermal core design. So in summary, modeling is useful. I would say critical for core design. Materials are process development, including what we are setting out to do, which is to develop digital twins of processes, and also for reliability assessment. And not only do we need multi-physics models, but we also need multi-scale models. Multi-physics because any interfacial phenomena is very complex interaction of multiple driving forces, including electrical, thermal, mechanical driving forces. So you need in multi-physics models, but you also need multi-scale models because the driving forces are applied at larger length scales, whereas the failure phenomena or other phenomena are occurring at much smaller length scales. And the physics and the math of process modeling is non-trivial. As you saw, generally the governing equations are not very well understood. They are non-trivial. And computational simulation of these moving boundary problems are also non-trivial. And ML modeling requires large data for fidelity, and in turn requires automated data generation. This is not well appreciated. In general, if you need large data, you need automated data generation. ML models are faster than computational models only when training time is not factored in. So if you factor in training time, then computational models based on theory may be faster. Training time drastically outweighs inference time. Thank you. I'll stop there.
Thank you, Ganesh. Very interesting. So now we have time for discussion. May I ask you first simple question? I have several, but I think this actually can lead us to bigger discussion, bigger scope directly related to digital twins. So I ask my question on, let's say, cost factor of modeling with respect to digital twin. A big motivation for moving towards in direction of digital twins is to reduce the costs of development, right? So design and process development. We started to do the cost analysis, and my question is, okay, the digital twins are not cheap. All this modeling is certainly not cheap. So how can we factor into our thinking?
So the way to think about it, going back to this this example that I described here, color mapping example that I described here, as if the time it takes for me to do extensive experimentation, here it is experimentation, right? I print out thousands and thousands of patches and measure the LAB values of every patch, the device independent color coordinates of every patch. And then I train a machine learning model. If the time it takes to train is unimportant, because what is important to me is that I want to be able to correct my printer quickly, then I think we can invest the time. So for example, if I have a process tool, I can put sensors on it. I can generate data, but I need to put sensors in probably lots of locations, but it's worthwhile if using that model that I generate is, it has to be done, decisions have to be done quickly compared to the time it took for me to build the model.
Yeah, it is the key thing. Thank you, Ganesh. Sadas.
Yes, hi Ganesh. Thanks for a very insightful presentation. I had a question, something building upon what Victor asked. Models, as you are very well aware, are not necessarily new. They have been around for a long time. What has changed that will make them more amenable to be used for a digital twin? Is it just that you will be running all of this? This is a leading question because I just want to make a point here as well. As Victor mentioned, running all these models take time and energy to compute because you are still talking about simulation-based data generation. So the digital twin is essentially generating all this data and having access to the data through this entity that you call digital twin, or is there some other utility for it in your mind?
So this is a slide that I showed. So that's, I don't know if you saw this. So
I missed the first few minutes.
No problem. So here, you can generate physical data in multiple ways, right? Through systematic experiments, DOEs typically, random tests, which are called as empirical data, or computational models. So models provide us data. Theory can also directly provide us data if we have an analytical solution.
Mm-hmm.
Then what we want is this. The only reason why we want, I hope you can see my mouse move on the screen.
Yes.
Yes.
So only reason why we want the machine learning models is because they're a lot quicker to evaluate compared to these models. That's the only reason.
On the fly.
On the fly.
But the
Near real
simulation
time.
will take the same amount of time 20 years back versus now, other than the computer hardware being faster.
Correct. Correct. So if at all possible, I would always use computational models and theory. That would be my first preference. Machine learning models is only as a last resort, simply because this takes so much more time for me to do. Experiments take even more time, right? So I want to avoid experiments.
Okay.
So if you have a grad student, you can have a grad student sit and measure 7,000 patches, color on 7,000 patches with a spectrophotometer. But that's time is not cheap.
Okay. Yeah. Okay. So it is more of a on the fly access to the previous simulations. What we used to do differently is we used to run these simulations and store them in some archives or some hard disk. Right now, these digital models will have access to that information from those simulations. Is that a fair statement?
That's a fair statement. The disadvantage, there are multiple disadvantages with digital twins. The model, like you described in your presentation, there is no causality. If, for instance, something goes wrong, I know I can tweak this weight or bias to get my model to fit, but I don't understand why I'm tweaking it. The causality is lost.
Okay. Okay. Thank you.
Thank you, Kanat, then Jim, then Henning.
Hey, so Ganesh, this refers to the last example you have on the 3D thermal plot. In any real microelectronic system the development, the architecture level, which is completely ignored by the electrical and the analysis that goes beyond that, provides a ton of rich data based on activity counts that point to the thermal, gives you a very excellent insight into the thermal events and the thermal emergencies and the hotspots. This data set is richly available. There's a ton of simulation data that precedes what is generated by the electrical phase that can be meaningfully used to speed up the model development and enrich the database. This is, why we need system scale, efforts. That's the point I'm trying to make. That would speed up the development of the models and including the machine learning model quite considerably. Bhagat and I have done a few things like this about 15, 16 years back.
Yes, you can, Kanad, without any doubt. So here it's based on some random power map associated with, in order to generate a generalized model. So the difference may be, I'm sure you've done this before, but the difference may be given a arbitrary three-dimensional package with arbitrary power maps, can you tell me a solution with arbitrary boundary conditions? Can you give me a solution in 0.0035 seconds? That's the question I would challenge you to ask.
So there is no such thing as an arbitrary 3D structure. Somebody developed that 3D structure architecturally, and there will be data. Yeah, I can promise you that. Architects do that,
No doubt. But here, at least, the aim was to build a generalized neural network model for arbitrary boundary conditions and arbitrary power maps. We can
Yeah,
exercise it.
I do get that. Yeah, that is going to be very challenging. If you don't have any prior data, any higher level data to guide your simulations, you have to do the exploration and find all the, pinch points.
I'm not an architect, but I think that's really the goal here, is to say that we can develop a machine learning model that can give you a solution for arbitrary power maps with arbitrary boundary conditions, Neumann boundary conditions and convective boundary conditions.
Yep. No, I do get that.
Okay, Jim is next. After Jim, Henning. After Henning, Andres.
Okay, Ganesh, very good presentation. Two questions. One on this graphic and the problem you were solving. It sounds like you were optimizing for the power delivery and the thermal the thermal response of the system, but it seems like there are some other constraints that you could optimize to, like the physical placement of chiplets. That it's like a bin packing problem, and then there's also like a network effect. Maybe you can just assume the backplane on the chiplet is not sensitive to placement, but in reality, there can be sensitivities where you want certain chiplets close to others and so forth. So this ends up being more dimensions of optimization. Am I correct in saying that these other factors were not considered in your optimization routines?
Actually, Jim, I probably didn't clarify this. There's actually no optimization here at all. All it is it's basically providing a machine learning tool, which then can be used for whatever optimization that you want to do.
Okay, but other considerations like networking were not.
No, they were not included here.
Okay. And then one quick question back on your previous graphic, slide 9, where you were talking about the systematic experiments, random tests, and computational models that led to physical data. I just wanted to point out that's a different view of the layout of data for a digital twin than, for example, the graphic that is used in the National Academy study that was recently published on digital twins, where there's actually a separation between, let's see, the virtual model, which is where modeling and simulation and computational simulations appear, and the physical model, which is where you have measurement and observation data. I'm sure this work was probably done before, but I just point that out. There's a different way of thinking about physical data versus which might be measured data of a physical system, and simulation data, which is of the virtual system.
Good point. That's why I put this A here, classification. So so this is a synthesis-oriented viewpoint. And I fully agree with what you're saying, but this is a synthesis-oriented viewpoint. From a synthesis point of view, if I'm trying to optimize a design, then whether I get the data to optimize comes from experiments or computational model, it's still a physical data.
Yes. And ultimately, the view from the National Academy report still requires this feedback loop between the physical and virtual world. So I think ultimately it's a matter of how you want to represent the trade-offs in the optimization process. So,
to go back to, I think your point is a very valid one. What I could also do is to create a loop between the systematic experiments and computational models and call that a digital twin as well as a sub loop here.
That's correct. I agree.
Yeah.
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 I think the intent is to really classify the data, right?
Yeah.
Not to show the loop or how it is used. I think.
Right. This intent is to classify the data.
And what is interesting in the model is the simplistic direct analysis that doesn't show up in the National Academy of Science model, unfortunately.
That's the most efficient.
Yep, it usually is, exactly.
It is very good. Henning.
Yeah, Ganesh, I want to ask you what you think about like other creative uses, I guess, of machine learning and AI for this type of problems. So I agree on the analytical solutions that they're wonderful. They can be evaluated very fast, right? But they're often a pain to derive. Like if I want to solve partial differential equations, maybe across multiple domains, I have to match all these boundary conditions. I end up with a large set of linear equations that depend on all of the parameters of the problem. So what we've been doing in the past, right, or so far, we may feed it into symbolic computation to get the analytical solution. It gets very messy, but can still be evaluated very, very fast. Right, and you may have been doing that, like you use Maple, and then they have it in MATLAB, they have it in Mathematica, so you can get analytical solutions very fast. My question is there a chance that an AI that is trained on solving math problems may be able to help us to solve analytical problems that are not considered to be tackled by humans? And could we build that into, say, digital twins? So you could have an AI-based system that derives maybe analytical solutions on the fly as the problem is changing. Boundary conditions may be changing, the whole problem setup may be changing, and then we could just generate analytical solutions on the fly and then rapidly evaluate and run the optimizations, etc. What do you think about such uses?
The closest I can come to, that's a very good question, Henning, and I think I'm fully with you. I think that's why I started with my first slide where I said if it's worth spending time to develop an analytical solution because it'll improve the fidelity and improve the accuracy for both reasons. The closest I can come to answering your question is this experiment we did with physics-informed neural networks. This is, more the title physics-informed neural networks is more recent, 2019, I believe. But if you look at the finite element community, this idea that I can use neural networks to represent spatial variation of arbitrary functions is very old. That's actually 1994 in finite element community. So you take a very simple problem. So here I have a PDE, right? So this is the closest I can think of to answer your question. Let me know if this addresses your question. So I have a simple PDE, and I have Dirichlet boundary conditions, and I solve it with varying architectures, neural network architectures here. These are approximating this domain with these architectures with unknowns, and then I have a finite element solution. At least in the near future, I don't see physics-informed neural network as providing me the intelligence or the speed to match what I can get with a finite element solution. At least in the near term, I don't see that. Now, this is a biased opinion, but that's my opinion.
But I mean, if I can solve this one analytically or semi-analytically, I could set up, I don't know, a Fourier-based solution.
Sure.
It may have infinite equations. I truncate it, and then I solve those analytically. I would get a very accurate solution, possibly very fast.
That's exactly right, and that's what we did here. So here I have a TSV. So I need to find the stressor on TSV. We actually analytically solve the stressor on the TSV and compare it to finite elements. And what you're seeing, let me blow this up a little bit. And this goes back to your point. Your point is very valid, by the way. So that's I'm fully in sync with your point. So here, these models that you see, these dark lines, are analytical solutions. And what you find is analytical solutions do really well if you can spend the time. It takes time. Like you said, this is a PDE. I need to analytically solve it. It's an infinite series. I truncate the series to some number of terms. I get a solution. It's actually as good as you can get with a finite element solution. It's worth investing the time to do that.
Okay, thank you. So I think there's a lot of applications we can still exploit, I guess, and make things better.
Thank you, Henning. Andres, we are going a little bit our time, but I think it's important discussions. Andres. Andres Torres, you're muted.
Sorry. Can you go to slide 9 again? So just from the point of view of using the data, right? These computational models to basically fill in a sample for the training data set. Typically, what you're trying to do is to kind of model the full system. Have you thought about one of the biggest challenges that we have in the digital twin is that sometimes there is data, but it's incomplete. So rather than focusing on creating first principle models to solve the problem, because that's what you need, right? You have the inputs and you have the outputs that then you can pass as training data. But if instead you can actually reduce the analytical problem by basically focusing only on subsections of the problem that then can be trained with the systematic experiments, and then it doesn't have to solve the full solution. It only needs to provide the a physically way of imputing the data that then can be used for machine learning models. Have you thought about pursuing that? Again, not trying to solve the full problem analytically, but actually just a portion of it that can actually enhance the machine learning process.
No, I have not done that, and the closest I've come to has a synthetic or generated data, which is basically using this data to generate additional data. That's the closest.
So, but in that case, you have to solve the whole problem in a way, right?
You need to tell me what your variable space is for me to sample. I'm constructing a response surface. I need to know the variable space over which I'm sampling in order for me to construct the response surface. So that span is critical. You need to define that. And your point is well taken. Yeah, go ahead.
Ganesh, can I interject for a second?
Sure.
So in my presentation a couple of weeks back, I showed a case in which we did the yield stress of pattern films. We use machine learning for the bulk material properties, and then for the thin films and pattern structures, we actually used analytical model. So we combined the two by using where data existed in lot, and where data did not exist, we used physics-based model. So we kind of hybridized it. That was just trying to address Andreas.
That's a great idea.
Right.
I think always, my opinion is, if you can do a theory, if you have an analytical model, that's always a very good start, because it'll take a lot less effort to generate data with analytical models.